Welcome to this TDS webinar. So it's our pleasure today to introduce Gergely Rost from the University of Szeged in Hungary. So Gergely is a major expert in dynamical systems and mathematical biology. So he started his career in Szeged, and then it became very international with stops in Gießen, Toronto, Arizona State and Oxford. And then he returned as a full professor in his university in Szeged. So also his CV in terms of service to the community is outstanding. For example, during the pandemic, he's been head of the Hungarian National Task Force in the battle against Corona, and in this function, key advisor to the Prime Minister. And he has also been heading the National Laboratory for Health Security. So needless to say that we're very happy that Gergely accepted to give a seminar here. And as far as I understand, it will be about how the analytic computations related to Hopf bifurcations can be simplified for classes of scalar delete differential equations. So Gergely, you have the word.
Yeah, thank you very much. Thank you for the introduction, and also thank you very much for inviting me to this seminar series. Yeah, in the past few years, most of my work focused on COVID, but still delay differential equations are my favorite topic. So I'm glad now I have the opportunity to talk a little bit about delay differential equations. And as I heard as Gabor told me that many in the audience will not be mathematicians, but I see the Italian experts on numerical Hopf bifurcation are joined, and so they know maybe more about Hopf bifurcation than me, but I hope I can still convey some useful information to everyone who is listening today. So as the title says, I will talk about Hopf bifurcations for some families of scalar delay differential equations. And the main point of the whole presentation will be that for some families, the generally very complicated calculations can be simplified to very simple conditions to decide if bifurcation is subcritical or supercritical. And from such a view, we can gain new insights and new information about the dynamics of this family of differential equations with delay. So let me just start with the very basic introduction about what is Hopf bifurcation. You can find it in many textbooks. This figure here, you can see I took from Wikipedia, for example. But generally, we have a dynamical system. You can think of a system of ordinary differential equations with a stable steady state, and the dynamics depends on some parameter, and if you change this parameter, then of course you change the eigenvalues at the linearization at the steady state, and sometimes these eigenvalues can cross the imaginary axis. That can lead to a loss of stability if steady states were all on the left half plane, but by change of parameters, they move to the right, then steady state will lose its stability. And in this case, we can observe appearance of a limit cycle via Hopf bifurcation. As you can see, for example, in this figure, this is before the bifurcation point when all eigenvalues were on the left. Then we have this spiral attraction to the steady state. But after the critical point, when we have two eigenvalues on the right, it is now repelling, and this circle here represents a periodic limit cycle, in this case, a stable periodic orbit. And this is a case of supercritical Hopf bifurcation, but we can also have a subcritical when the limit cycle appears on the other side, when the steady state is still stable. And in this case, the periodic orbit itself is unstable. And this is a normal form written in a complex variable, so for a planar system. And then for the normal form, so the normal form is a simplified form of a nonlinear system, and we make, idea of normal forms is that we make a change of variables and nonlinear transformations, which simplifies the expansion of the right-hand side. So we have the fewest non-zero coefficients as possible. And this, for Hopf bifurcation, that we see is the normal form. And then the supercritical or subcritical is depending now on the real part of this parameter b here, which is sometimes also called as first Lyapunov coefficient. So this is for planar systems. We can write it in a complex variables, and we can do normal form reduction and find the real part of this b and decide bifurcation is subcritical or supercritical. So for higher dimensional systems, this is fairly straightforward for planar systems. Of course, if you work with a higher dimensional system, then you can use projections to invariant manifolds. I took these examples. I thought maybe people familiar maybe with this paper or this topic, but the picture here is very general, so it's not related to the particular model. But this is just an illustration what you have to look at if you work in a higher dimensional system. Then you have a two-dimensional invariant manifold with the equilibrium here in the center. And now you have this stable or unstable periodic appearing on this manifold. So you can move to higher dimensional spaces and still study Hopf bifurcation. So now let's move to delay differential equations. So let's start with the simplest delay differential equation, just scalar linear with one single delay. And we know very well if the delay is small. Of course, the delay is zero, then it's trivial exponential decay. But even for small delays, we still see similar behavior. By increasing the delay, actually about 1 over e, but in this case, for tau equals 1, we already see oscillatory solutions, but still damping down to 0. And at pi over 2, we have cosine and sine as particular solutions of this equation, and we can have this periodic, and for tau passing through being larger than pi over 2, we can see this growing oscillations. So in the linear system. So actually that the delay can induce oscillations in systems which would be not oscillatory in the absence of delay. This is a very, very old observation. This is one of the first examples from 1948. And actually this paper was written about ecology and written by George Evelyn Hutchinson, who was also called the father of modern ecology. And he was concerned about oscillations observed in ecological systems, so a population of some species fluctuating. And he came out with this idea that if we introduce a time lag, so here capital N is the size of a population. So if the rate of change of a population size depends on a past value, so with some time delay, then we can have oscillations. And it is described here a very intuitive way that K would be here also called carrying capacity, so a steady state when a population is at a stable positive level or at a constant positive level. And then if we look at the growth of a population, and if you have this time delay, you can pass over this K, overshoot, and then later coming back, but again go down below K and so on. So basically, it's an intuitive description of how oscillations generated by delayed negative feedback. This was already kind of realized heuristically by ecologists at that time. And they also say the longer the delay, the larger oscillations we can expect. And for small values of the delay, oscillations will die out. And then there is a very interesting footnote also in this paper. So this was just kind of heuristics about what behaviors we can expect with the introducing a time delay. But there is a very interesting footnote here also, which was written by Lars Onsager, who 20 years later received the Nobel Prize in Chemistry. So apparently Hutchinson consulted about this issue with Onsager, and so the equation they were particularly looking at is this one. You can see it here or here on the top. Basically, it's a logistic equation when for the second term, here we introduce a time delay. That's in their notation, this is in the index, but it's just y evaluated at t minus tau in our understanding. And actually, Onsager looked at this one, and they find this critical, he found this critical value, pi over 2. So here they discovered that for delay, well, the parameter here in front of the of y is normalized to 1, and then just a single parameter delay. So in this case, pi over 2 is the critical delay, where oscillations appear. And of course, it's related to when the linearization, it's now linearized at equilibrium 1, we lose its stability at pi over 2, and that corresponds to appearance of oscillations. They didn't call it Hopf bifurcation, but basically we know now that happens here. At pi over 2, we have Hopf bifurcations for this delayed logistic equation. And that's, yeah, so if you linearize at steady state 1 and write a characteristic equation, we can simplify this critical value pi over 2. And if you now look at some numerical solutions of delayed logistic equation, that for less than pi over 2, we see oscillations damping that and disappearing. But for larger than pi over 2, we have this, even if you start from close to the steady state, near 0 with very small perturbation, you will see this limit cycle behavior. And even so, what was already recognized by Onsager here is that this last sentence here in the footnote is that when the delay is large, then you can see a succession of high peaks alternate with very right truths. So basically, from this equation, you can expect these sudden bursts in the population shooting up for short periods of time. That's exactly what we can see here. So I don't know how they figured this out in 1948, but I think it's quite impressive. And especially they were not mathematicians. So there were two examples, also biological examples, when Hutchinson thought this delay can be relevant. One was about Daphnia population, in particular because the fertility of a female Daphnia can depend on its past exposure to past population densities. Also, another example here was mentioned was field mice, when we could see these irregular fluctuations in population. But there was still no direct derivation of this equation here from biological principles. And actually that was raised, this question was raised in this paper here, Mathematical Ecology via Mechanistic Models by Gergely and Gergely, that we should give, it was not just the delayed logistic equation, but about logistic equations in general, that how can we derive logistic equation from biological principles? So, and it stands for the delayed logistic equation as well. Introducing the delay there could produce oscillations. So it produced the phenomenon we observed, oscillations in some populations. It was not clearly connected to the biology. If I go back to this equation, like you can see here, a product of a delayed and non-delayed terms. It's not so easy to explain, but it's not related to birth and death of the individuals and so on. So basically, there were many follow-up works on deriving logistic equations from biological principles in a mechanistic way. And here I just showed a couple of examples by Arinov and Volkovich, for example, called alternative formulation of delayed logistic equation. That's slightly different from Wright's equation or from the previous delayed logistic equation, or by Lindström from more general class of chemostat models under some assumptions reduced to this one. Or with my work with Nakata for SIS type epidemiological model gives rise to a similar logistic delay equation, or also for a cell population cell biology model can be eventually reduced to a delayed logistic type equation. But these ones actually don't produce the same oscillations as the previous one. So now, if we're looking at equations of this form, and just let me introduce the general mathematical framework. So, for example, this equation here, this delayed logistic equation, is a element of this class of equations when right-hand side is depending on the history of this function, this x sub t. We also refer it to sometimes a segment of the solution. X sub t is defined here. So x sub t at theta is just x evaluated at t plus theta, when theta runs through this interval from minus tau 0 of the delay, maximal delay in the equation is minus tau. And so then now f is a mapping from these functions, the history functions, to r to the real, or rn if we have multiple variables. And generally we're looking at these equations as dynamical systems in the phase space of continuous functions on this interval minus tau 0. And this way we can define semi-flow on this Banach space with the sup norm. And then you can think of it, you have some initial function, it's your initial data, you start your solution, and then at every time instant t, you're looking at this window of the solution of length tau, going from t back to the past t minus tau. And what you see in this window is the current state of your system as a dynamical system in the function space. Or if you can shift it back to original interval, then your dynamics changed from this function, you move to this function at time t. So this is just the dynamical systems point of view. So also for delay differential equations, so we have seen it was observed many decades ago that it can induce, the time delays can induce oscillations. And it was later, of course, understood that Hopf bifurcation is a typical way that by changing the delay, introducing or changing the delay can generate oscillations and periodic solutions. And that there are many methods how you can look at Hopf bifurcation for delay equations. This is a kind of very old book. It already has a chapter, Theory and Applications of Hopf bifurcations, particular chapter about delay, how to compute Hopf bifurcations for delay differential equations. There is a whole book concerning this problem, and there is another very seminal work by Teresa and Magayesh from 30 years ago. So there are several methods. The keywords here: center manifolds, bilinear form, spectral projection, and so on. And also these are the analytical tools, but of course there are many numerical bifurcation tools now. Many of the development in this area is due to the group in Italy. So if you look at the literature, just make a search, Hopf bifurcations for delay differential equations, you will find hundreds of papers. Of course, there are many nonlinear delay differential equation models in all fields of science, not just in engineering, but in ecology, biology, models in economy, and so on. So there are many nonlinear DDEs worth of studying, and many papers are looking at the Hopf bifurcations in these nonlinear systems. And so usually the way these papers go is that consider one nonlinear DD, model of some phenomena, we linearize at a steady state, look for critical roots of the characteristic equation. You want to identify situations when a pair of roots crossing the imaginary axis. And then you compute this first Lyapunov coefficient to decide it is supercritical or subcritical. So generally speaking, the first step is easier, finding critical cases when eigenvalues crossing. But computing first Lyapunov coefficients usually is much more elaborate. And here I just show one typical example, but you can see many of them. Like in a paper, such a paper has the theorem like this, that at some critical delay, we have a Hopf bifurcation, and it is subcritical or supercritical, depending on the sign of this value, real part of this kind of C1. So what is C1? In this example, what I cut it from, this was a model 2 variables, and we have nonlinear term here. And usually for this C1, you have to now understand that this is positive or negative, the real part of C1. You can find usually this formula for C1. And now you have some new letters here. We have G, and G with 2 indices. So these G's are coefficients from the normal form. When the like G, the indexes means the power of Z and the power of a conjugate of Z. Like G to 1 will be the coefficient of Z squared times conjugate Z. So anyway, how you calculate the coefficients of the normal form, papers give you more formulas for that. And then here some new letters appear, like these W's. These W's actually coefficients of the expansion of the system on the center manifold. So my point is that it's a very, very, very long calculation. You start from your model parameters. I want to decide if bifurcation is subcritical, say B equals 5, D equals 0.2, mu equals something. I'm interested in bifurcation is subcritical or supercritical. Then you can go through all these steps. And it's quite cumbersome, but you get some answer. Eventually you find a number and you just say real part is positive or negative. So, but this doesn't really give you an insight how this criticality depends on original model parameters. So you can calculate in all particular cases. So that's the question I'm concerned with now is, can we tell the criticality of the Hopf bifurcation in terms of original model parameters in a simple way that I can understand if I change one parameter, will the criticality of bifurcation changes or not, without repeating this calculation for all particular cases? And the answer will be I would call it a small yes or a partial yes. So for some simple families, we can do this. We tried for more complicated families, but I will talk a little bit about it later. So basically, we look at these equations. I will call it Wright type equations because I will show some results about Wright's equation, which is a particular case, the delayed logistic equation, also called Wright's equation. But anyway, we're just looking at the scalar equation. Delay here is normalized to 1, and this will be our bifurcation parameter mu. So by time rescaling, you can either change the time delay or you can change parameter in front. It's equivalent. And f is some nonlinear function. And if you have just this single term, nonlinearity with the delay term, I will call this Wright type equation. So just a smooth function f now, and I consider its expansion, looking at this B and C coefficients in the expansion. And so this is a kind of a whole bifurcation theorem, which is now valid for the whole family. So basically, the critical parameter value is always pi over 2 plus 2k times pi. K is some integer, can be even negative. It can go other way also. And basically, this is the result. What we derived is that the case bifurcation, so which correspond to this mu k critical value, supercritical if we have this inequality, and subcritical if we have the other way around. And then C and B are just the coefficients from the expansion, and h of k here is this function here, function of k, which is independent of the equation. Okay, so in the next figure, I'm just showing you h of k. So this blue curve is this function h of k. We have these dots because we interested only at values at integers. So we're interested only in these dotted values. And basically, the previous theorem says that we're just looking at C over B squared. So C and B are the terms from the expansion. And we compare C over B squared to different values of H. And that tells us everything about the bifurcation is subcritical or supercritical. In particular, if for some K, H of K is below the C over B squared. So like, let's say C over B squared is 1.4, then the zeros bifurcation is supercritical, the others are above it, so others are all subcritical. If C over B squared is, say, 1.6, like here, then for all K, these points are below C over B squared, so then all bifurcations are supercritical. So basically, just look at C over B squared and it tells you everything. And this is how the calculation works. So basically, I took it from the paper here. Basically, we followed, I don't go into details how this works, but this is exactly following steps of Faria and Magaya's normal form calculations, which is in the left, and then you arrive to an expression here. And the thing is, if you hear this, you can see his B and other stuff, they all depend also on, they depend on K, so which bifurcation you're looking at, and of course depends on the nonlinearity. But if you just substitute in this general form, after some manipulations, and you can factor out positive terms, basically you have this tilde. This tilde means having the same sign because we're interested only in the sign, or basically it means it's a factor of the other term by some positive factor. So we can omit positive factors, and that's just all the mathematics we do here at this step is basically simple algebra, just factoring out positive terms. And eventually you reduce to something which is exactly depends on, the sign depends on C minus this HKB squared. So I have to tell you, we had great difficulties publishing this result because the referee said it was rejected twice, the paper, and by the same reviewer. Ironically, from two different journals, we got the same reviewer because reviewer argued that, which we see in the left side, this is well known how you calculate the bifurcation. But we still see value in looking at it for the whole family in this view. Because what people did before for particular equations, they calculated it for particular values. But if you just do some more looking at in a more general framework, a more general setting, you get this formula, which is, we argue, very useful. And I will show you we can derive many information, general information, and also information for particular equations also looking at it like this. So just look at some of the examples. So Wright's equation, so this is an equivalent form of the delayed logistic equation. By this change of variable, it can transform into this form, which is of the form we're looking at. So our F nonlinearity F is now E to the X minus 1. And here we just say B equals 1 over 2, C equals 1 over 6 for this one. So we immediately get all Hopf bifurcations are supercritical, which, of course, again, it was known before. But if you look at Ikeda equation, it's again a common equation from optical resonator systems. Again, you just look at this expansion of sign, B equals 0, C equals minus 1 over 6. Again, all Hopf bifurcation supercritical. So, and we can construct examples like this one, polynomial equation, just choosing the cubic term properly and the quadratic coefficient. This one has two subcritical bifurcations, others supercritical. Or you can construct a completely subcritical polynomial equation, again, a cubic, which has all bifurcations as being subcritical. And here is an example of the branches. This is Ikeda equation, or all supercritical. The other are example, all subcritical. So here these branches correspond to stable periodic solutions. Here these branches correspond to unstable periodic solutions. And we can even characterize all possibilities. So this is the condition, C less than H0 times B square. If C and B are such like that, we have a normality like that, then all bifurcations are supercritical. Or we can have one point when it flips, switches up to this point, subcritical, then supercritical. And we have basically these five possibilities up to all bifurcations subcritical. So looking at it this way, we could characterize all possible bifurcation sequences. For example, we know it's not possible like we have two supercritical and then one subcritical and two supercritical again, switching back and forth. This is not possible. This result shows that. It's only these five configurations possible. Here, this is just the numerics for the right equations in the sixth figure. But these five configurations are all what can happen, and we can show very easily. Look at the nonlinearity and immediately tell you which configuration the bifurcation sequences are in. So now we can combine this insight with what is called a Cook transformation. So now imagine we have, assume we have a periodic solution with period capital T. Then the observation by Cook was that then if we look at this Q of T, this function, it's also a periodic solution. You just differentiate and substitute, and it's a periodic solution of the same nonlinear equation f, but with this parameter in front of it. So instead of mu, we have now the new parameter here. And you can check this function is indeed periodic with this new period now, t over lt plus 1. L is any positive integer. So basically it says if you have a periodic solution, by this simple transformation, you can find more periodic solutions, and you can tell the period of the new one relative to the old one, as well as, of course, this is a periodic solution for the same equation, but with a different parameter. So anyway, we can make this mapping of triplets. So given a parameter mu, period t, and the periodic solution p, we can construct another triplet. We call it Cook mapping with a different parameter, different period, and a new periodic solution. So, and actually we can show that this mapping, these branches, local Hopf bifurcation branches to other branches. In particular, if we looking at the bifurcation K and choose some L, then this CL map, it brings the branch to the K plus L's branch. We can show this by using uniqueness of the, it's local uniqueness of Hopf bifurcation branches. So now we can use this relationship now between, connect this to the criticality of the bifurcation, because criticality also tells us that which side of the critical parameter periodic solution appears. So for example, if we are in the case that basically it says that this condition, from previous results now, we know bifurcations supercritical, then we can estimate the period of the emerging solutions. And simply because we know if all bifurcation is supercritical, that if I look at the bifurcation branch at mu k and I map the branch to k plus L, then the new parameter of the transform periodic solution will be on the right, will be larger than this critical value, because that's supercritical. And then from this relation, just rearranging, I get an estimate for the period. Okay, here now, eta is the difference of our parameter from the critical parameter. So if I move away from criticality, I can estimate the parameter of the periodic solution along this branch. And if we have all subcritical bifurcations, I can give an upper estimate. And if we have a switch, some bifurcations are supercritical, some subcritical, then for these indices, some indices, I can give upper and lower estimates for the periods. So here is an example, or here is a graph showing that one example when it's a subcritical bifurcation, and I think it's used, we use the BIF tool to calculate the Blue one is the numerically approximated period, and the dashed are analytic estimates from these inequalities. So they're quite sharp analytic estimates. So now we can do this the other way around too. So if we have information on the periods, assuming we have information on the periods, then we can draw conclusions about the criticality. So if we know this period is smaller than at the critical point, then we know that particular bifurcation will be subcritical. So now we can look again this particular Wright's equation and its relation to some of the most well-known and very old conjectures about the dynamics of this equation. One is called Jones conjecture. Jones conjecture said that, so we have the first bifurcation point at pi over 2, that for mu larger than pi over 2, there is a unique slowly oscillating periodic solution. So slowly oscillating means that the distance between subsequent zeros or with subsequent crossings of the steady state is less larger than the delay. So that type of solutions emerge first. And the conjecture was there is a unique slowly oscillating periodic solution for all larger parameter values. And there is another conjecture which is still open, that the period along this branch is monotonically increasing. So, and this monotonicity was shown for a very small interval in this paper. It's a proof of Wright's conjecture. I didn't tell you what Wright's conjecture is. So Wright's conjecture is that all solutions converge when this mu is smaller than pi over 2. So when the steady state it's also phrased in a way sometimes that when it's locally stable, then it's globally stable, which was also, again, another long-standing conjecture for 60 years, has been solved not so long ago. So anyway, what we can do now is we had this partial result for this interval that periods are monotone increasing, show for a short time or a short interval after the critical value, but by Cook transform, we can transform it to other branches. And what's interesting is that, of course, the further you go in a bifurcation, the longer this interval will be, because the length, the width of this interval is scales with k. So actually we have larger and larger intervals for other branches when the period length increases monotonically. So about absence of folds, now I recall another related paper by Jean-Philippe Ressard. I took this picture from this paper. So basically this is illustrating what we're talking about. So we have first bifurcation point at pi over 2, and we have a branch of periodic orbits. And basically you can think of Jones' conjecture is that this branch is going indefinitely to the right, and the solution is slowly oscillating periodic solutions are on this branch. And when it is unique, the slowly oscillating periodic solution, then it cannot have a fold. Like here in the figure, you can see the branch is folding back. So it can be shown that on this branch, solutions remain slowly oscillatory. Then this is not possible, or that is what you want to exclude, this fold. And it has been solved so far, or solved in the proof of Jones' conjecture paper. So now we know that these folds, they don't exist for the first branch at least. And then you can see this other structure, this called isola, which just means just slowly oscillating periodic solutions would emerge from somewhere else, not from the steady state. And for slowly oscillating periodic solutions, this is also excluded by proof of Jones' conjecture. So basically how it connects to our results is that by Cook transform, you can transform isolas from different oscillations. So we can exclude also isolas of rapidly oscillatory periodic solutions because if we could transform it to slow ones, and slow ones don't exist. But still, it's not sufficient to show that there are no folds in other subsequent branches, which corresponds to more rapidly oscillatory solutions. So to guarantee that, we would need the monotonicity, which was conjectured, monotonicity of the periods. However, we have a monotonicity of periods, at least for small intervals. Like I go back to on these intervals, we know that the period increases monotonically. So we can guarantee that there are no folds on these intervals, at least for later bifurcation points and for rapidly oscillating periodic solutions. So at least for close to the critical value, the branches of rapidly oscillating solutions cannot fold back. That also follows from this. So I think lots of useful information followed from this, looking at these four possible bifurcation sequences. And it also relates to another concept, which is called the negative Schwarzian derivative, which is this expression for a smooth function. But what I just mentioned about this is in this paper, there was another conjecture, which means that for this in family of right-type equations, if F satisfies negative Schwarzian condition, means this S of F is negative, then we have right conjecture, analog of the right conjecture, also can call it generalized right conjecture, that local stability of the equilibrium implies its global stability. And this is still, this we know for Wright's equation, but we don't know it for general equations with negative Schwarzian. This is still a conjecture. But if we look at now what the negative, because we have here third derivative and second derivative in Schwarzian, just like in the what we need for the bifurcation. So now we can connect the two. And if negative Schwarzian is negative, we can easily see that C must necessarily be smaller than B squared. All bifurcations are supercritical. We can also see that if in particular special case when second derivative vanishes, sign of third derivative determines the bifurcation. But overall, one way to disprove this conjecture could be construct a subcritical bifurcation. So if you find an example, negative Schwarzian giving rise to subcritical first bifurcation, then we had local stability of steady state alongside with the limit cycle. So that would, global stability would not be true. So, but now we know at least these kind of counterexamples cannot exist. So it's again, just looking at it this way, we kind of get strengthen the conjectures a little bit. So now finally, I will show another example of blowfly equation. So this comes from a series of experiments in the 50s done by Australian entomologist Nicholson on blowfly populations. So this is the blowfly in question, and they can cause significant damage to the wool of sheep. That's why it was concerning to study their population dynamics. And this is from laboratory population experiment. And here we can see this irregular behavior. There were many experiments in very different conditions, but this is just one of them. And sometimes it was observed by Nicholson that population can oscillate even in constant environment. And that was a bit puzzling at the time. So people thought in a constant environment, population should converge to the carrying capacity of that environment, but here we had seen these large spikes. And actually there were many attempts. Sir Robert May tried to fit the delayed logistic equation to Nicholson's data, and it would give a reasonable fit. But again, there are two problems with it. One is that neither the time delay. So the idea was here that this oscillation generated by a maturation delay. You can see the other curves for eggs laid. And clearly when eggs laid, sometime later, you can see the adult flies. So this time maturation delay from egg to adult must be important in this generating these oscillations. And the maturation, so you cannot connect the delay in this fitting to delay the real maturation delay. So there were some other attempts, other models I show here, which again try to fit to blowfly data, but both attempts has the other problem that in the blowfly data we have these double peaks. So it's not these nice regular oscillations, but very often you see two peaks within a period. And then eventually this model was introduced in 1980 in this paper, Nicholson's blowflies revisited, and the authors here looked at this delay differential equation. Here we have instantaneous mortality term, and we have this delayed reproduction or delayed recruitment term with time delay tau, and it's this nonlinearity as this shape, this unimodal shape, and this non-monotone shape can be explained by intraspecific competition. And you can easily generate solutions like this, very similar to Nicholson's. These are numerical solutions. And you can also generate, of course, periodic solutions as well. So this is just a summary, very brief summary of what is really well known about the linearization and bifurcation of the blowfly equation. So this is the equation. Look at the steady state N star, linearize it, we get this characteristic equation, and we can find the critical values in the parameter and the delay in this case when we have a pair of eigenvalues. Now this is of course a transcendental equation, but at every critical delay, a pair of eigenvalues crossing the imaginary axis. If I plot this on this parameter plane, this is just one quarter of the parameter plane, the interesting one. By increasing the delay, so here both parameters on this axis are proportional to the delay. So if I increase the delay, I move along straight lines. And whenever I cross such a curve here, I have a Hopf bifurcation. So these numbers denote how many eigenvalues I have with positive eigenvalue, with positive real part. So on the right-hand side of the complex plane, on the right half plane. So 0 corresponds to stability, and a positive and 2, 6, 4, 2, 4, 6 all corresponds to instability of the steady state. And this region here is characterized by this condition. This is what we call absolute stability. If I increase the delay here, I just remain in the 0 domain. But in this other region characterized by p larger than e squared gamma, if I increase the delay, I will cross these curves. These are the Hopf curves when I have imaginary eigenvalues, and we have a sequence of Hopf bifurcations. So if you look at what was in the literature about again, the question is, the bifurcation is subcritical or supercritical. So do we expect stable periodic oscillation of the population, basically, via Hopf bifurcation? If supercritical, then yes. So it was studied in this paper. And again, the condition, here you can see how complicated this is. This is the first Lyapunov coefficient. So this C10, we mentioned C10 before. So you have this very large formula, and also N star is the steady state. So you have to make many steps. Also delta is a derived parameter from others. So if somebody looks at this equation and gives you, okay, this is my mortality rate, this is my production rate, and so on, is the bifurcation supercritical? Then you have to make lots of calculations, substitute everything into this formula. The derived parameters, you have to derive them, and so on. And then you see it's positive or negative. So using a similar approach as before, we could show that it's always supercritical. And basically, it's not just the theorem here was concerned only about the first bifurcation point, tau 0. Okay, for the subsequent critical delays, tau 1, tau 2, and so on, formula would be, it was not in the paper, but it would be even much, much longer. So, but we could show that it's always supercritical, and not just the first one, but all of them for all positive k. And I don't detail here, but again, using this general normal form method, basically we could arrive after lengthy calculations, we could arrive to this expression that Lyapunov coefficient has the same sign as this expression here. When B, we have to calculate B also from this n star is the steady state. But we could also show by some inequalities that this is always has the same sign. So no matter what are your parameters, particular parameters here, as long as you are in this domain when you can have stability loss, the bifurcation is always supercritical. So there is no need in the future for Nicholson-Blofeld equations. We want to look at the bifurcations. You know, it's always supercritical. Whenever it exists, it's supercritical. So basically, this what I wanted to show you today. These are published in these 2 papers. So with this, thank you very much for your attention.